Folks, in this problem we're given a semi-ellipsoid which will serve as our surface, and it's got an upward facing normal vector, and we're given a vector field that we can imagine it sitting inside of, and then we're asked to use Stokes Theorem to compute the following integral. In this video I'm not really going to do an interpretation of the problem. We'll just go ahead and solve it. If you have any questions about how we could interpret this question, feel free to let me know. But let's go ahead now and sketch our region. So what I've done was sketch the ellipsoid and included a few normal vectors on this. Let's go ahead and put a few points on here. The height of this ellipsoid maxes out at 1z is 2. And this down here at the base is just the unit circle. So again, we could imagine, at every single point along the surface we're computing the curl, and the curl is related to with the vector field, and that's going to give us some vector pointing outward. So there's three vectors at play here in a way. We've got the vector in the vector field. Maybe that's the vector in the vector field. That's f of some point on the surface a, b, c. And then we have the curl of f at some point a, b, c, which is the new vector that's formed at that point. And then we're going to be asking to what degree is the green vector in alignment with the red normal vector, and that's what we get when we take the dot product. As far as interpretation goes, like I said, I'll leave an interpretation of that to somewhere other than this video. But we don't want to do this calculation. I guess we could. It would involve coming up with a parameterization for this ellipsoid. But we're told to use Stokes Theorem. And Stokes Theorem says that rather than computing the curl dotted with this normal vector, instead we could go ahead and work solely on the boundary of this curve, which is this C that I just sketched right here. So let's go ahead and give Stokes Theorem. So rather than computing the surface integral as we were originally given, we're going to compute the line integral around the boundary C. This will make things quite a bit easier. You can see that this problem, if you try to tackle it directly, has a fairly nasty z component. However, our curve sits in the xy plane, and so when we parameterize our curve, our z component will just be 0, making this far easier to work with. So I'd now like to give a parameterization of C, our boundary. So let's use the standard parameterization for when we have a circle for this curve. So we could say that this is going to be the curve cosine t, sine t, and then 0, because our z component is always 0, and that's actually why Stokes' theorem is so beneficial in this particular instance. So we're getting ready to do a line integral calculation. For that we will need r prime of t. We'll also need to express our vector field in terms of t. Let me do that. So folks, I'm going to quickly change this. I went ahead and did the full parameterization, but notice that because the z component is parameterized by the function 0, then we just end up with cosine squared t, sine squared t, and 0, making this far easier to work with. One thing I just remembered, I forgot to give the interval the parameterization. So this is for a circle, and so we could parameterize it from 0 to 2 pi. So now we're ready to evaluate the line integral, which will give us the equivalent surface integral by Stokes' theorem. So let's go ahead and calculate and compute this integral. And so we end up with an answer of 0. Let me know if you have any questions on this, folks, and I'll see you in the next video.